folks. I'm going to make a video. This is the first few homework questions from the Unit 5 test review day. We're starting with page 110, number 22. And there's kind of a similar question, I believe, asked on the next slide as well. So this question asks which functions are differentiable at x equals 1. So what that means, differentiable just means, does the derivative exist? So we can take a look at the function itself. For the derivative to exist, first of all, the value of the function must exist at that point. If there's no point defined on the function at x equals 1, then you obviously can't find the slope of the tangent at that point because there's no point at x equals 1. Sometimes we could get things so if f at 1 does not exist, or f prime at 1 is undefined. So first we're going to check if f at 1 exists, or g at 1, or h at 1. So for a, here, f at 1 does not exist. So here, if we subbed in a 1 on the denominator, we would get 3 over 1 if we subbed in. So that is undefined. That's a restriction on my original function. There would be an asymptote at that value, so you can't take the derivative where there's an asymptote because the function doesn't exist. And then let's take a look at b. So here, g at x equals x minus 1 over, and then I would factor this one, x plus 6, x minus 1. So we could reduce that, but there's a hole at x equals 1. So that tells me that g at 1 does not exist. So of course, the derivative at that point doesn't exist either. You can't take the derivative if you don't even have a value on your function at that point. So let's take a look at the next one, h at x. I'm going to rewrite this as x minus 2 to the exponent 2/3. And here, h at 1 actually does exist. So h at 1, that would be negative 1 to the exponent 2/3, which is 1. So h at 1 exists. We do have a point there. Let's try taking the derivative. So h prime at x would be 2/3 x minus 2 to the exponent negative 2/3 times the derivative of the stuff inside, which is just 1. So that is 2 over 3 times the cubed root of x minus 2 squared. And this would exist. So h prime at 1, we could sub in a 1 there, and we aren't getting any restrictions. So that would be 2/3. So here it is differentiable for h at x equals 1. The last function, m at x for part D, I would look at this as probably a piecewise function, and you would have to be able to find the derivative of each piece of this. We won't have absolute value functions because we haven't really dealt with those in class, so this won't be covered on your test. But just maybe to rewrite this, you can look at this either graphically or using a piecewise function. Maybe graphically might be a better example. So this is the absolute value function, which is like when we get a v, and it's shifted 1 to the right and 1 down. So I'm going to have it at this point and it's got a stretch factor of 3. So that's what that function looks like. And basically, we would have to figure out for x is less than 1, this would have one equation here. So what would the equation of that function be, of that line? And then it would have a different linear equation. And because the slopes of those are different at each point, here the slope would be -3, and here the slope would be 3. So because they're different slopes, we can't figure out what the slope is exactly at that point. So this would be not differentiable. I think probably easiest for you to show that from a graph, but like I said, the absolute value functions will not be on the test for Unit 5. This is very similar. So this is one where we're looking at what would the restrictions be where we could not find the derivative of a function. So here we know that the restrictions for f at x, I could rewrite this, that x would not equal 0 or 1/4. So those would be definitely restrictions of where I could not find the derivative of this function because those points don't even exist on the function. If I found the derivative, I do want to check and make sure that there's no extra restrictions on just the derivative that weren't restrictions on the original function. So here I'd have the denominator 4x squared minus x times the derivative of the numerator, which is 0, minus the numerator, which is 3, times the derivative of the denominator, which is 8x minus 1, all over the denominator squared. So 4x squared minus x squared. So then I get -3 times 8x minus 1. I'm going to common factor back out that x. So it would be squared, and then 4x minus 1 squared. And then just kind of looking at this again to show that the restrictions on this, where the denominator would be 0, are the same as the original function. So x is not equal to 0 or 1/4, and those are the only points where this function would not have a derivative. Okay. I'm going to skip b, but it's very, very similar. You just find the restrictions on that original function, and be careful because you can factor and reduce because you're going to have a hole in that function. But any restrictions on the original function f would also be restrictions on the derivative because you'd have a hole there. There is something a little bit interesting that happens with this one, with the square root, in terms of what this would look like. So this would be, I'm just going to factor this, x minus 6, x minus 1 to the exponent 1/2. And I know that x minus 6 times x minus 1 has to be greater than or equal to 0 because I have this function in the square root. So I have to have the values of that have to be greater than or equal to 0 because I can take the square root of 0. So you guys can do this with a chart or a sketch to solve this inequality, but I know that this is going to be a parabola with points with intercepts at 6 and 1, and it's opening up. So when would this be greater than 0? I would say that x is less than or equal to 1, or x is greater than or equal to 6. So these are the values of x that this function is defined for. Less than or equal to 1 and greater than or equal to 6. Now, if I take the derivative of this function, I want to see, are there any additional restrictions on the derivative? So 1/2 and then x squared minus 7x plus 6 to the exponent -1/2. And then I'm multiplying by the derivative of the inside stuff, which is 2x minus 7. So here I get 2x minus 7 on top, and on the bottom I have 2 times the square root of x squared minus 7x plus 6. So now I still want this stuff in the derivative or in the square root sign to be positive because I can't take the square root of a negative number, but I also cannot have this equal to 0 because now the square root is on the bottom. So the restrictions on the derivative are that x squared minus 7x plus 6 is greater than 0. Not equal because it's in the denominator. Before, it could be equal to 0 in the original function because we could have that equal to 0. Now this square root is on the bottom, so we can't have it equal to 0. It's just greater than. So that's going to change my restrictions to x is less than 1 or x is greater than 6 because I don't want it touching that 0 point because now it's on the denominator. So that's where this one would be differentiable. Oh, I'm sorry. I just noticed that this says where is it not differentiable? So not between, I was saying where it was differentiable. So between 1 and 6 inclusive is where that's not differentiable. Okay, this one, we want to rate this as a composition of two smaller functions. So there's a few different ways to do this, and it's just trying to get you to recognize the chain rule and see how that can be applied here. I might say let f at x equal 2x minus 3. Then g at x would be f at x to the exponent 1/2 plus 5 f at x, right? So this would be 1/2 f at x to the negative 1/2 times the derivative of f at x plus 5, and then this would have an exponent of 0 times the derivative of f at x. And we know that f prime at x here equals 2. So we could sub back in. This can be, it's an important concept to understand. Most people wouldn't do a derivative like this unless it was particular kinds of word problems where you had maybe multiple functions in real life dependent on each other, that you had kind of a function of for one variable and then that was a rate of change of another variable. So here this would be 1/2 and then 2x minus 3 to the exponent negative 1/2 times 2 plus 5 times 2. And we can simplify that just a little bit. Here, given the function x equals e to the x over x, solve for f prime at x equals 0. So let's take a look at what the derivative would be. F prime at x is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So I would common factor up on the top, e to the x, and then x minus 1 over x squared. So here, if I want to find where the derivative equals 0, f prime at x equals 0, where x equals 1. We know that e to the x, remember e is just a number, like 2.7 to any exponent won't give you a 0, but this could be 0 where x equals 1. So this would be likely a turning point, which is a max or a min of the function. And that's the significance because it has a horizontal tangent.